So today's problem is going to be search in rotated sorted array. Now, this problem is actually remarkably similar to the find minimum in rotated sorted array problem. So if you've not done that problem, I recommend you do that problem first and then come back here. It'll be linked in the description. So similar to that problem, we're going to be given a rotated array as our input, and it's going to be rotated an unspecified amount of times. So in this case, we have 3, 4, 5, 6, 1, 2. But what's different is that this time we have a target, and our job is to return the index that houses this target if it exists, and if it doesn't exist, we are to return -1. And once again, all the elements in the sorted array are unique, so the only possibilities is that either there's one answer or there's no answer. And it is asking us to do this question in log of n time, which again is another huge hint for us to do binary search. So let's see how we're going to bend binary search to solve this problem. Well, let's say this is our input. The first thing we want to do is probably initialize our low and high pointers to the first and the last elements, right? We're going to call this nums, and high is going to be at the length of nums, -1. And then we're going to write a while loop with an unspecified exit condition. So I'm going to put true for now, because I'm not too sure when we're going to exit. So in this case, we have a low here and a high here, and then we'll calculate a mid. This is just standard binary search things. Plus high divided by 2. So let's say our target is 1. How are we going to look for that in our input here? So as we know, half of the array is ascendingly sorted and the other half of the array is not. The half of the array that is not sorted properly is the subarray with the flip here. And the flip is when we go from standard ascending order to suddenly decreasing to the smallest element and then continuing to increase again. So just knowing the structure of our input, it's pretty easy to find out which half of the array actually stores our target. Our goal here with binary search is to continuously eliminate half of the array by narrowing down which half of the array actually contains our target. And then we do that continuously until we narrow down to just a single element. And if that element is the same as target, then we will return the index of that element. Otherwise, we can finally conclude that target doesn't exist here. So to start, before narrowing it down, we should check target with the value at mid here, because there's a chance that we just get lucky and without even narrowing it down at all, we find our target in mid. So we'll write a simple if clause. If nums at mid is equal to target, then we found our answer, right? We can simply return the index, which is mid. Right, that's the easy clause. Otherwise, if we know the left side of the array is sorted, then we know for sure the right side of the array is not sorted, right? So if the left side of the array is sorted, and target is within the range of this, then we want to eliminate the other half of the array, right? So if nums low, well, the value here is less than nums mid, well, I guess less than equal to nums mid, right? Because, well, in the event of an input of something like this would be our low, this would be our high, our mid would be here. And if you were to separate them out, you would have left of mid, which is like this, and then right of mid, which is this, right? And you would say that this subarray is sorted, right? So we'll say that if nums low is smaller than nums mid, like in this case, then of course, this left subarray is sorted. And in the equals case as well, if both mid and low point to the same number, then we can also regard this single element subarray to be sorted, right? In both cases here, the left subarray is sorted. So after passing this check, we know that the left side is sorted, and we also want to know whether target falls within the range, you see? We want to know whether target is greater or equal to nums low, and whether target is smaller than the number at mid, right? So let's think about this clause. Let's just change our target so it's a little bit easier to visualize. Let's say our target is 3, right? 3 is going to be within this range because 3 is greater than equal to the number at low, yet at the same time is less than the number at mid. So 3 would exist somewhere in here, which it does, right? Whereas our original example with 1 here is going to say, well, yes, in this input, the left subarray is indeed sorted. However, when I try to check this, is target greater or equal to low? Well, it isn't. 1 is not greater or equal to 3. So that means that our target is not in the left subarray, which is a correct deduction. Now, say it were the case that our target is in the left subarray, then we want to move our high value, right? So should we move the high value to mid or mid -1? Well, the answer is we want to move it to mid -1. And that's because we had this check earlier, which checks the value at mid. And if the code has made it this far, it means that this check has failed, which means that mid cannot be our target, which is why we are no longer considering mid as part of our search space. And instead, we're moving high over here. So let's have a look at what happens now. I'm going to calculate my mid value, and it's going to check, hey, our mid turns out to be the same as our target, and that's going to give us the answer. But that's not always the case, right? Let's go back to our original state. If my target was 1 instead, then what happens? This check's going to fail because 1 doesn't fall in range as discussed earlier. Then we would need another branch that lets us explore this area, right? So I could write else, since we know that our result is in this space specifically, excluding mid. we're going to move low to mid plus 1. And then it's going to find our answer at mid, next iteration, and we'll get our result. And that seems to work pretty well. But now I want to ask you, do you see a problem with this code? Because there's actually quite a major bug here. And I'm going to show you that bug with a different input. Let's say this is our input. Low is here, high is here, and mid is here. Okay, it's going to do the first check. Is the left half of the array sorted? Well, clearly it's not. So that means our target must be on the right. And so the else block executes and we will move the low pointer over here. Do you see the problem? We just narrowed our search space to where our answer doesn't exist at. Now the reason is we came to the wrong conclusion. It is true that the left half of the array is not sorted here. The problem is that this is a different structured input entirely. This if else really only works if I change the clause to first checking again if nums low is less than or equal to nums mid. And more importantly, if target is not in here, right? If target does not fall under this range, then this would work. We actually haven't covered the clauses where the flip happens in the left side of the array instead of the right. So we actually need two more conditions. We have to check whether nums mid is less than or equal to nums high, and the target falls within that range. The range of nums mid and has to be less than or equal to nums high. So if the right subarray is sorted instead of the left, this, and target falls under the range of this subarray, then we want to move the low pointer up to mid plus 1. Now the last scenario, which is the scenario that we're looking at right now, is a scenario where the right half is sorted, not the left, and target does not fall in the range of the sorted array. This target does not fall in the range of this sorted array. So we have to search in this half of the array. And in this case, we want to move our high down over to mid minus 1, right? The high is equal to mid minus 1. And you can already see, right? We have repeated logic here, these two, and these two have repeated logic, and we can actually group them up, so it's a little bit easier on the eyes. But there's one thing we quite haven't figured out yet, and that's the exit condition for this code. So let's try searching for a target that doesn't exist, so we know when to call it quits. Let's say my target is 0 here. Well, let's have a look at what happens. We're first going to check whether mid is same as our target. It isn't, and in that case, we find out that the number at mid is smaller than or equal to the number at high, which means that the right half is sorted. So now we only concern ourselves with these two clauses, right? Now the next question we ask is whether our target falls within range of mid and high. Does 0 fall within the range of 2 and 5? Well, it doesn't. So surely it is the case that, if anything, it has to be in the unsorted half of the array. So this block will execute, and high would be moved down to mid minus 1. And then the same thing happens. We calculate mid. We find out that, hey, this time we have this subarray and this subarray. And the subarray that contains only one element, 6, is actually the sorted one, right? Because 6, 1 is not a sorted array. So we have this subarray here, which we consider sorted. So now we're looking at this clause and this clause, right? And then next, we check whether 0 falls under the range of 6 and 6. Well, it doesn't fall under this range, right? So this clause executes. We move low up to the next index, right? So now both low and high point to the same index. There is still a possibility that our target is at this index, right? So we still want to check this. We don't want to call it quits yet. Like, for example, if our target was 1, say, then our answer would be here, and we would have to check this clause, otherwise we would have missed out on a potential answer. So it's going to calculate mid, and it's going to check this value and find out that, hey, 1 does not match our target 0. This branch is going to execute, which is going to move our low pointer up to the next index. And then at this case, our search space contains 0 elements, and we can exit our search. And since we'll be exiting when low is greater than high, so that means we're going to be continuing so long as low is less than or equal to high, right? It's the inverse of our quit condition. This is our continue condition, which is what we're going to write in our placeholder just now. And once we exit, of course, it would mean that this block never executed, which means we never found our answer, in which case we can safely return -1. So let's write our code in the editor, shall we? And it'll be the cleaned up version of this thing without so many clauses like this. So this is basically the code that we had earlier in the Blackboard. And if you run it, it is correct. It does work, but I'm just going to clean up the code base a little bit. So we can see that we have these checks, right? And this one checks whether the left half of the array is sorted. And this one checks whether the right half of the array is sorted. And all I'm going to do is just kind of group them into these two major branches. So one that executes if the left is sorted. And within that, I'm going to check whether target falls within the sorted left half. And in that case, we have to move our high pointer down. Otherwise, we don't really need any of this anymore, right? We can get rid of this basically. In this class, we don't have to write it so explicitly. We can just change all this to an else. Well, it's the same thing for here basically, right? Let's run this again. And there you go. Here's our final solution. Let's talk about time and space complexity then. For time complexity, we're going to be running binary search, which is, as we know, is a log of n algorithm. So we're going to execute this loop log of n times. And every operation that we have here, the additions, the divisions, and all of this, there's no operation here that is not over one time. So the time complexity of this is actually how many times we're looping through this, which is log of n, multiplied by the cost of running each operation in the loop, right? Which is 1. So that's why it's simplified down to just O of log n. And as for the space complexity, we have 3 variables here, low, high, and mid, but they all just store integers basically. So our space complexity is over 1. And that's about it. Okay, bye.